for a second and picture an atom. What do you see?
Hmm.
Probably, a tiny solid ball, maybe smaller balls orbiting it, that classic picture.
Yeah, the sort of billiard ball idea. It's what science gave us for ages.
Exactly. But
Yeah.
what if that picture, it's useful, sure, but what if it's just fundamentally not right at the deepest level?
Well, yeah.
What if the shape of matter isn't solid? What if it's something, well, stranger, more like waves and chance?
That classical view, those solid spheres. It works fine for, baseballs,
Right,
planets.
right. Big stuff.
But you dive down to the quantum scale, and reality just completely shifts. The source material we're looking at today really just blows that simple picture apart.
It does. It takes you right into quantum mechanics, doesn't it?
To show how these really weird rules actually lead to the shapes we talk about for atoms, like that spherical look.
Okay, so that's our mission for this deep dive then. We want to pull out the core ideas from these sources.
Yeah, the really key stuff.
Like that mind-bending wave-particle duality, the link between energy and frequency, this wave function idea.
And how probability isn't just predicting things, it is the reality down there.
Exactly. So by the end, you'll hopefully see why thinking of atoms as hard little balls, well, it just doesn't capture the quantum truth.
It's quite a journey, really, from the most basic property, that dual nature, through the math describing its state, to understanding how those rules create the actual forms, the building blocks of everything.
Yeah, we'll trace that path. Wave nature, energy as frequency, then the probability landscape of the wave function.
And finally, how symmetry ends up dictating the shape. All right. So let's just jump right in, headfirst into the quantum pool. This idea that particles aren't just particles.
Okay, so the really fascinating starting point, and our sources dig into this, is Louis de Broglie.
De Broglie, right.
He proposed something truly radical back then, that everything, and I mean everything, even tiny things we definitely think of as particles, like electrons,
also behave like waves. It's not, one or the other depending on when you look.
It's both at the same time.
Exactly. Both simultaneously. It's fundamental. A particle isn't just a point. It has this inherent wave character.
Okay, that's already pretty weird. A particle is a wave, but if it's a wave, it has to have wave properties, like frequency.
Precisely. And this is where it gets really interesting, as the source material highlights.
Oh, on.
That wave tied to the particle, it has a frequency, usually written as EA, the Greek letter nu.
Okay.
And this frequency isn't just some random characteristic, the Planck-Einstein relation. Maybe you've seen E.
Ah, yes, a classic. Energy equals Planck's constant times frequency.
That's the one. It's a cornerstone. It tells us the particle's energy, E, is directly proportional to the frequency of its associated wave.
Directly proportional. So higher energy means a higher frequency wave.
Exactly that. And the sources really hammer this point home. Talking about a particle's frequency is basically talking about its energy.
It's not just that they're linked, they're almost the same thing.
In a fundamental quantum sense, yes. They're two sides of the same coin, inextricably linked. Energy, which feels very particle-like, how hard it hits, is defined by frequency, which is totally a wave-like concept, how fast it oscillates.
Wow. Okay. So matter is secretly a wave. Its energy is its frequency. How on earth do scientists even describe that? You can't just draw it easily.
No, you need a different kind of description entirely. And that's where Erwin Schrödinger comes in. 1926.
Schrödinger, the cat guy.
Slight chuckle. Well, yes, famous for the cat thought experiment, but his huge contribution here was the equation, a mathematical wave equation specifically for describing this wave-like nature of particles.
Okay, an equation.
And the solution to this equation is what we call the wave function, usually written as psi, the Greek letter E.
Psi. Okay, and what is psi?
Think of it as this complex mathematical object. It holds essentially everything you can possibly know about the particle's quantum state.
Everything, like its momentum, energy.
Yes, and crucially, where it might be found.
Ah, might be. That sounds fuzzy, uncertain.
It absolutely is, and this is a critical point our sources really stress. The wave function, E itself, it's not something you can directly observe.
You can't measure it, like with lab equipment.
Nope. It exists more in a mathematical space describing the potential.
Okay, wait. If I can't measure itself, how does it help? What can I get from it that connects to the real world, to experiments?
Ah, good question. What is physically meaningful, what you can relate to measurements, is the square of its magnitude, written as absolute value of psi squared.
Okay. And that tells me?
That tells you the probability density.
Probability density. So where the particle is likely to be.
Exactly. It doesn't say the electron is here. It says if you look here, this is the probability of finding it.
So where E is a big number, there's a high chance of finding the particle.
Precisely. High value, high probability. Low value, low probability.
So quantum reality isn't like a sharp map. It's more like a weather forecast map showing probabilities.
That's a decent analogy, yeah.
Yeah.
It's a fuzzy landscape of probabilities until you actually make a measurement. That active measurement is what seems to collapse the possibilities into one outcome, but the wave function itself gives you the odds.
Wow. Okay. Matter is a wave. Frequency is energy. Location is probability. How does that strange combination get shaped into something structured, like an atom? How do we get shapes out of probability waves?
Right. This is where forces come into play. And crucially, the symmetry of those forces.
Symmetry.
Yes. The shapes we associate with atoms, like that basic spherical idea, they arise because the main force involved has a particular symmetry. It's a spherically symmetric potential.
Okay, unpack that. Spherically symmetric potential.
Think about an atom. You have the positive nucleus at the center, right?
Yeah.
And a negative electron.
Attraction.
Exactly. An electrical attraction pulling the electron in. Now that force, it really only depends on how far away the electron is from the nucleus.
Just the distance, not the direction.
Correct. The pull is the same strength if the electron is, say, 1 nanometer away to the north or 1 nanometer away to the east or south or west. Only distance matters. That's spherical symmetry.
Ah, okay. The force is the same in all directions at a given distance, like a perfect sphere.
Exactly. And when you have a situation like that, symmetric in 3D,
You'd use spherical coordinates in the math.
you got it. Makes the math much easier. Instead of x, y, z, you use distance r from the center, and then two angles, theta and phi, to specify the direction.
Right. Like latitude and longitude, but for math.
Sort of, yeah.
Yeah.
And our sources show that when you solve Schrödinger's equation for a particle in that kind of spherically symmetric force field,
The wave function.
it naturally separates. Mathematically, it splits into two parts. One part depends only on the distance, r. We call that the radial part.
Okay.
And the other part depends only on the angles,
Mhm.
non-fold. That's the angular part.
Radial and angular parts.
Yeah.
And the angular part that controls the shape.
Exactly. And these angular parts, they aren't just any old functions. They are described by a specific set of mathematical functions called spherical harmonics.
Spherical harmonics. Okay, the name definitely sounds right. Symmetrical.
Slight chuckle. They are. Very elegant mathematical functions. And according to the sources, these spherical harmonics are precisely what define the characteristic shapes of atomic orbitals.
The SPDF orbitals? Those funny balloon shapes from chemistry class?
Those are the ones, they come directly from the math of these spherical harmonics, which are the angular solutions to Schrödinger's equation in a spherical potential.
Okay, let's take the simplest one. The s orbital. That one always looks like a sphere in the diagrams. How does that fit?
Good example. The s orbital corresponds to the absolute simplest spherical harmonic. This particular function has the same value no matter what the angles ekatai and vix are. It's perfectly symmetrical in all directions.
Completely uniform, angle-wise.
Exactly. So because the angular part of the s orbital's wave function is described by this totally symmetric spherical harmonic,
Then the probability must also be spherically symmetric.
you got it. The probability density cloud for finding that Cheikis electron is also perfectly spherical around the nucleus.
Ah, so the spherical nature isn't a hard shell. It's a spherically shaped cloud of probability.
Precisely. The electron isn't on a surface. It's somewhere within that fuzzy spherical region. The math tells us the probability distribution.
And the chances are usually highest closer to the middle for the simplest orbital, right?
Generally, yes. For the lowest energy state, the one's orbital. It's all dictated by the interplay of the radial and angular parts of the wave function.
So it's a probability map, defined by the forces and the wave nature, and the other shapes, the PDF.
They come from the other, more complex spherical harmonics. Those functions do depend on the angles, which leads to the lobes and rings and more intricate probability distributions you see for P, D, and F orbitals.
But they still come from the same basic framework. Wave function, spherical harmonics, probability.
Exactly the same framework, just different mathematical solutions within that framework corresponding to different angular momentum states.
Okay, so let's try and wrap this up for you listening. We started by questioning that simple billiard ball atom.
Yeah, that'll take.
We took a dive into the quantum realm, found out matter is a wave.
Whose energy is its frequency.
And its location isn't fixed, it's described by this wave function, which gives us a map of probabilities at.
And And then we saw how the basic symmetry of a force, like the electric pole in an atom,
Being the same in all directions.
shapes that wave function. Its angular part is described by these special functions, spherical harmonics.
Which create the probabilistic shapes we call orbitals, including that fundamental spherical shape of the s orbital.
Right. So the real aha moment here, coming from these sources, is really getting that our everyday intuition about solid stuff just doesn't work down there.
Yeah, it breaks down completely.
Matter's form isn't about surfaces. It's about its wave nature, its energy state, and these probability distributions that are shaped by the forces.
The shapes aren't boundaries, they're more like probability weather maps, showing where the particle is most likely to be.
That's a great way to put it. It's a shift from certainty and solidity to likelihoods and wave behavior.
Which leaves us with a pretty mind-bending thought to end on, doesn't it?
It really does.
If the fundamental reality of matter is based on probability waves, and their frequency is their energy, what does that really tell us about, well, the substance of the universe itself?
Yeah, and how does something as seemingly simple and elegant as spherical symmetry in a basic force, how does that give rise to all the incredible complexity and structure we see around us, all built from these uncertain, fuzzy, probabilistic foundations?
Definitely something to ponder.